The sun's magnetic shield is disintegrating. Right now, a massive plasma hemorrhage is terrifying scientists worldwide. At exactly midnight on February 2nd, 2026, something unprecedented happened. The sun fired not one, not two, but three monster explosions in a single hour. An X-8.1 flare, the most powerful solar blast in years, was followed by two more, back to back to back. Here is what has scientists panicking. This was not random. This was a warning shot. Buried deep inside the sun, a mega sunspot called Active Region 4-366 is doing something space agencies have never seen before. It is building power, stacking energy, and the next explosion could be 10 times stronger. Right now, billions of tons of superheated plasma are racing toward Earth at millions of miles per hour. Radio blackouts have already begun. Radiation storms are incoming. And the probability of a Carrington-class event, the kind that could collapse power grids worldwide, just jumped to levels not seen in our lifetime. Is this the sun's final warning? Or has the main event already begun? February 1st, 2026, 2300 UTC. Active Region 4-366 begins destabilizing on the sun's surface. Space weather monitoring stations across the globe detect the first signs of extreme magnetic instability. Within minutes, the most powerful solar flare sequence in years begins to unfold. At exactly midnight Coordinated Universal Time, the first explosion erupts. An X-8.1 class flare, the strongest solar blast of the current cycle. Energy equivalent to billions of nuclear bombs is released in a single, violent burst. The flash of radiation travels 93 million miles and strikes Earth's upper atmosphere in just 8 minutes. But the sun is not finished. Within the same hour, a second flare explodes from the identical location, an X-1.5 flare. Then a third, an X-2.8 flare. 3 monster explosions in approximately 60 minutes. Space weather agencies scramble to process data that defies their models. The timing is not coincidental. For the previous 24 hours, Active Region 4366 had been firing warning shots. Over a dozen M-class flares rippled from the sunspot. An X-1.0 flare punctuated the buildup. Scientists recognized the pattern. The sunspot was loading energy like a coiled spring preparing to release. What makes this sunspot so dangerous is its structure. Active Region 4366 is not the largest sunspot ever recorded. It is unusually compact and extraordinarily dense. The magnetic field configuration displays intense mixing in the intermediate region, directly between the positive and negative polarities. This central mixing position is critical. When magnetic complexity concentrates at the edges of a sunspot, energy release is limited. When mixing occurs in the middle, the sunspot can draw power efficiently from its entire magnetic structure. The result is explosive potential that far exceeds what the sunspot's size would suggest. Data from solar observatories reveals another disturbing characteristic. The flare sequence displays long-duration signatures with multiple energy spikes. This pattern indicates sustained magnetic reconnection rather than a single explosive release. Scientists monitoring the X-ray flux recognize what this means. Active Region 4366 is not winding down. The triple flare sequence appears to be preparation, not conclusion. The sun is just getting started. NASA's Solar Dynamics Observatory captures the aftermath in stunning detail. The 304 angstrom imagery reveals a massive coronal mass ejection exploding outward from Active Region 4366. Billions of tons of superheated plasma erupt into space at velocities exceeding 1 million miles per hour. The scale of the eruption dwarfs Earth by comparison. Initial trajectory analysis offers a partial relief. The bulk of the plasma appears directed slightly off Earth's direct path, launching at an angle away from our planet's orbital position. But scientists issue an immediate warning. This does not mean safety. The physics of coronal mass ejections are more complex than simple direction. An explosion this close to an Earth-facing position generates shockwaves that expand in all directions. Even when the primary plasma cloud misses, the flanking shockwave can still deliver devastating impacts. The last major geomagnetic storm originated from a similar solar position. It still overwhelmed power grids and triggered aurora visible across the continental United States. Space weather experts emphasize a critical distinction. The X-class designation of a solar flare does not directly translate to the strength of its coronal mass ejection. Four variables determine the actual impact on Earth: velocity of the plasma cloud, angle of approach toward our planet, magnetic field strength within the ejection, and most critically, magnetic polarity. A negative polarity, coronal mass ejection, connects directly with Earth's magnetic field. This connection opens a pathway for charged particles to pour into our magnetosphere and trigger severe geomagnetic storms. A positive polarity impact deflects more easily. The difference between these outcomes determines whether Earth experiences a minor disturbance or a catastrophic event. Scientists await coronagraph imagery to confirm the precise trajectory and arrival timeline. The data will reveal velocity, density, and magnetic configuration of the incoming plasma. Until that imagery arrives, predictions remain uncertain. One calculation requires no additional data. An explosion of this magnitude, this close to an Earth-facing position, guarantees an incoming shock wave. The only question is how powerful that impact will be when it arrives. The moment the X8.1 flare peaks, radio communications begin failing across half the planet. The National Oceanic and Atmospheric Administration issues an R3 radio blackout warning. This is the second highest alert level on the 5-point scale. High-frequency radio signals degrade or vanish completely across the sunlit side of Earth. The geographic impact zone centers on the Pacific Ocean. The flare peaks directly over Hawaii, Australia, and New Zealand. Eurasia catches the edge of the blackout zone as dawn breaks across Asia. For aircraft crossing the Pacific, the timing could not be worse. Commercial aviation relies on high-frequency radio for communications over oceanic routes where satellite coverage remains limited. Pilots lose reliable contact with ground control. Air traffic management centers scramble to maintain situational awareness as their primary communication links fail. The Federal Aviation Administration issues advisories for trans-Pacific flights to expect communication disruptions. Maritime vessels face similar challenges. Ships crossing the Pacific lose contact with shore-based stations. Emergency communication channels experience interference. Coast Guard operations in the affected zone report degraded coordination capabilities. The R scale measures radio blackout severity from R1 to R5. An R1 event causes minor signal degradation. An R5 event eliminates high-frequency radio communication entirely for hours. The current R3 classification indicates wide-area blackouts with significant operational impacts. The X8.1 flare nearly pushed conditions to R4 territory, which requires an X10.0 flare to trigger. What alarms communication experts is the duration. Radio blackouts have persisted continuously for over 24 hours across affected regions. Each new flare from active region 4366 refreshes the disruption. Normal solar flares produce blackouts lasting minutes to an hour. This sustained degradation indicates ongoing solar activity that shows no signs of stopping. Emergency services in affected regions adapt to degraded communications. First responders switch to backup systems. Hospitals verify landline connections. Utility companies test alternative coordination channels. With active region 4366 still magnetically unstable, additional radio blackouts are expected with each subsequent flare. The communications disruption is not ending, it is just beginning. Earth barely recovered from the strongest radiation storm in 23 years. An S4 event on the 5-point severity scale had just subsided when active region 4366 unleashed its XXX class sequence. Now scientists brace for another surge of high-energy particles racing toward our planet at nearly the speed of light. The physics leaves no room for doubt. An explosion of this magnitude virtually guarantees a radiation storm. Space weather experts calculate less than 0.1% probability that proton flux levels will remain stable. When billions of tons of plasma erupt from the sun, a massive shockwave of protons, electrons, and ions radiates outward in all directions. Earth sits directly in the path. The S scale measures radiation storm intensity from S1 to S5. An S1 event causes minor impacts to satellite operations. An S5 event threatens astronaut safety and damages spacecraft electronics. Scientists predict this incoming storm will reach S2 at minimum, with S3 or higher increasingly likely based on flare intensity. The most alarming possibility is a ground-level enhancement event. Under normal conditions, Earth's atmosphere absorbs incoming solar radiation before it reaches the surface. But when particle flux reaches extreme levels, high-energy protons traveling near the speed of light punch through the atmospheric shield. These particles trigger cascading collisions that shower the surface with secondary radiation. A ground-level enhancement requires protons at 500 mega-electron volts. Only the most powerful solar explosions produce particles at these energy levels. The XXX class sequence from active region 4366 may qualify. The implications extend across multiple sectors. Aviation faces the most immediate concern. Passengers and crew on high-altitude flights receive significant radiation doses during severe storms. Airlines reroute polar flights to lower latitudes, where atmospheric shielding is stronger. Medical devices present another vulnerability. Pacemakers and implanted electronics can malfunction under intense particle bombardment. Hospitals in affected regions prepare contingency protocols. Aboard the International Space Station, astronauts monitor radiation levels and prepare shelter procedures. Their position outside Earth's protective atmosphere makes them particularly vulnerable. The proton storm clock is now ticking. The incoming plasma wave threatens infrastructure that modern civilization cannot function without. Critical infrastructure like power grids, satellites, GPS networks, and telecommunication systems all face potential disruption or failure. The interconnected nature of these systems means a single point of failure can cascade across continents. Power grids represent the most critical vulnerability. When charged particles from a coronal mass ejection interact with Earth's magnetic field, they induce electrical currents in the ground. These geomagnetically induced currents flow through any long conductor, including power transmission lines. Transformers at the heart of electrical grids cannot handle these unexpected surges. They overheat. They fail. In worst-case scenarios, they explode. History provides a sobering precedent. In March 1989, a geomagnetic storm collapsed the Hydro-Quebec power grid in 92 seconds. 6 million people lost electricity. The blackout lasted 9 hours. The solar storm that caused it was significantly weaker than what active region 4366 is capable of producing. Aviation authorities have already demonstrated their concern. In late 2025, Airbus grounded 6,000 aircraft after solar activity affected flight control systems. The XXX class flare sequence raises those concerns exponentially. Aircraft navigation depends on GPS satellites that become unreliable during severe space weather. Autopilot systems receive corrupted positioning data. Pilots must revert to manual navigation procedures. Satellite operations face direct assault. Communication satellites in geosynchronous orbit sit outside Earth's protective magnetic field. Solar radiation damages their electronics, degrades solar panels, and disrupts the signals they relay to ground stations. Weather satellites, military reconnaissance platforms, and the satellite internet constellations that increasingly connect rural areas all become vulnerable. Financial systems depend on precise timing signals from GPS satellites. Stock exchanges require synchronization accurate to microseconds. Banking transactions rely on satellite communication links. A severe geomagnetic storm does not just threaten convenience, it threatens the mechanisms that move money around the world. Oil and gas pipelines face accelerated corrosion as ground currents flow through their metal structures. Electric vehicle charging networks experience disruptions as the grid fluctuates. Everything connects. Everything depends on everything else, and everything is now at risk. In September 1859, the Carrington event struck. The most powerful solar storm in recorded history slammed into Earth with devastating force. Telegraph systems across Europe and North America failed simultaneously. Operators received electrical shocks from their equipment. Telegraph papers burst into flames. Aurora Borealis appeared as far south as the Caribbean. In 1859, the world ran on steam and horses. Telegraph represented the cutting edge of technology, and the Carrington event caused inconvenience and confusion. Today, the same storm would trigger catastrophe. Modern civilization runs on electronics. Power grids span continents. Satellites coordinate everything from navigation to banking. Computer systems control water treatment, hospital equipment, and food distribution. A Carrington-class event would not merely inconvenience society, it would paralyze it. Scientists typically estimate Carrington probability at 0.1% in any given year. Those odds just change dramatically. The XXX class flare sequence demonstrates that active region 4366 possesses the magnetic complexity and energy reserves for extreme eruptions. Current probability estimates have jumped to 10% or higher. Some researchers suggest the actual figure may be significantly greater. The mathematics of solar flare escalation explains the concern. Flares typically build from a baseline activity level, amplifying 100 to 300 times in strength during major eruptions. The triple sequence established a new baseline near high M-class levels. If the next eruption follows the standard amplification pattern, an X50 or X100 flare becomes mathematically possible. An X50 flare would produce a coronal mass ejection capable of overwhelming Earth's magnetic defenses entirely. That could cause complete GPS failure across hemispheres, widespread transformer destruction across power grids, and satellite damage requiring years of replacement launches. Radio blackouts could last days rather than hours. Economic impact estimates for a Carrington-class event range from $1 to $2 trillion in the first year alone. Full infrastructure recovery could require 4 to 10 years. Some damaged components simply cannot be manufactured quickly enough to restore normal operations. Active Region 4366 has not finished erupting. The magnetic structure that produced the triple flare sequence remains intact. The sunspot is still cooking. The Carrington question remains open. Active Region 4366 remains magnetically armed. The intense mixing structure in the sunspot's intermediate region has not dissipated. The engine driving the triple X-class flare sequence continues operating at full capacity. Scientists monitoring solar imagery confirm that the conditions for additional major eruptions persist unchanged. The National Oceanic and Atmospheric Administration Space Weather Prediction Center maintains around-the-clock surveillance operations. NASA's Solar Dynamics Observatory streams continuous data from its orbital vantage point. International space weather agencies coordinate observations and analysis across time zones. The Global Monitoring Network operates at maximum alert status. Coronagraph imagery will reveal the critical details scientists need: the precise trajectory of the coronal mass ejection, its velocity as it races through interplanetary space, the magnetic configuration that will determine how severely it impacts Earth's magnetosphere. Until that data arrives, predictions remain educated estimates rather than certainties. Current calculations suggest a 24 to 48-hour window for potential coronal mass ejection arrival if the plasma cloud is Earth-directed or delivers a strong flank impact. Geomagnetic storm conditions will likely trigger aurora visible at unusually low latitudes. Residents across the northern United States and southern Canada should watch for unusual lights in the night sky. Government agencies issue preparedness advisories for affected regions. Backup power systems should be tested. Emergency communication plans reviewed. Basic supplies verified. These precautions may prove unnecessary, but the cost of preparation pales against the cost of being caught unprepared. Space weather prediction remains an inexact science. Unlike terrestrial weather forecasting, which benefits from centuries of observation and dense sensor networks, solar storm prediction relies on limited data and incomplete understanding. Surprises remain possible in both directions. The storm could dissipate before arrival, or it could intensify beyond current projections. For researchers, the event offers an unprecedented scientific opportunity. Data gathered during this sequence will improve models and predictions for decades to come. The full moon rises in Leo as Earth awaits the incoming plasma wave. The celestial alignment adds cosmic resonance to an already extraordinary moment. Active Region 4366 continues its magnetic convulsions. The sun is still cooking. The next eruption could come at any moment. 3 X-class flares in a single hour. The strongest radiation storm in 23 years. radio blackouts spanning half the planet, and a probability of Carrington-class catastrophe higher than any point in living memory. The events of February 2nd, 2026 have rewritten the space weather record books in ways scientists are still processing. The numbers tell a story of unprecedented solar violence. An X8.1 flare, followed by X1.5 and X2.8 in rapid succession. Over a dozen M-class flares in the preceding 24 hours. Continuous R3 radio blackouts affecting aviation, maritime operations, and emergency services across the Pacific and Eurasia. Proton radiation levels triggering the strongest storm classification in more than 2 decades. But numbers alone cannot capture the significance of what is unfolding. Right now, somewhere in the darkness between Earth and Sun, billions of tons of magnetized plasma race toward our planet at over 1 million miles per hour. The shockwave from the triple flare sequence will arrive within 24 to 48 hours. Whether that impact triggers a minor geomagnetic disturbance or a civilization-threatening electromagnetic pulse depends on variables scientists cannot yet measure. Velocity, trajectory, magnetic polarity. The answers travel with the plasma cloud itself. The vulnerability of modern civilization has never been more starkly exposed. Every system humanity depends upon connects to infrastructure that solar storms can damage or destroy. Power grids that span continents. Satellites that coordinate navigation, communication, and financial transactions. Computer networks that control water treatment, hospital equipment, and food distribution. The technology that defines contemporary life is precisely the technology most threatened by extreme space weather. In 1859, the Carrington event disrupted telegraph systems and amazed observers with spectacular aurora. The same storm today would collapse power grids, disable satellites, and trigger cascading failures across interconnected systems. Recovery timelines would be measured in years rather than days. Economic damage would be measured in trillions rather than millions. The infrastructure humanity built during a century of relative solar calm was never designed to withstand the sun's full fury. Active Region 4366 has not finished its assault. The magnetic mixing structure that generated the triple flare sequence remains intact and dangerous. Solar observatories detect no signs of decay or stabilization. The sunspot that terrified scientists with 3 monster explosions in 1 hour could produce something far larger in the hours and days ahead. The waiting game continues. Monitoring stations track incoming data. Emergency managers review contingency plans. And billions of people go about their daily lives, unaware of the plasma wave hurtling toward their fragile technological world. Is this the sun's final warning before returning to quieter activity? Or is the triple X-class sequence merely the opening act of something far more destructive? The sun is still cooking. The next course could change everything. And humanity can only watch, wait, and hope that when the plasma arrives, our civilization proves more resilient than the physics suggest.